Good morning, everyone. Welcome to now webinar number 31. Thank you for coming back. We were supposed to take a 3-month break, which turned into more of a 6-month break. So thank you for joining us. Today we're going to have Charles from Toray that's going to be going over submerged MBR membranes. Now, we have done membrane bioreactors before. We've touched a little bit more on general process and how they operate. Now we're going to kind of drill down a little bit more onto the specifics. We did take a bit of a break, and thank you, Charles, for getting us back in here and actually reminding us that we were going to start. So with that, we can get started.
All right. So thank you, everyone. Really appreciate all your time. We know this will be a quick one, so I'll jump right into it. And also thank you very much for AWC putting this together. We really appreciate the opportunity. So looking at real quick, I want to jump into, I won't spend too much time on this, but I do want to give everyone a real quick idea how big Toray really is. It was one of the funny things I didn't even know when I first started working for the company. It's a massive, over $20 billion a year company. The biggest sections are actually, funny enough, carbon fiber and some other ones, but the environmental and engineering, you'll notice that's right where our membranes fit in. And it's a big aspect of the environmental side of Toray. So it's not going anywhere, and we just like to show that obviously a big company with good, strong backing. We'll touch a little bit more on the membrane R&D technology in general and how Toray fits into it as well. As you can see, in 1953 was when RO started. And then in 1961, JFK approved desalination as kind of one of the national projects, given that the importance of water. In 1968 was when Toray got involved on the RO side of things, and it's just expanded from there. And you can see in the 90s, we joined on both the UF and the MBR technologies as well. So just to show how long we've been in the membrane side of things and lots of experience with all of our products. All right, now into the good stuff. Submerged membrane bioreactors. I know there has been another webinar on MBRs before, so I'll kind of touch a little bit on it. But essentially what we're looking at here is a conventional tertiary process on the top. You've got your clarification, then your aeration basin, followed by secondary clarification and your sand filter. Obviously, your sand filter is going to be your tertiary process, but as we all know, sand filtration, while it provides good quality effluent, isn't the greatest quality effluent depending on what you want to do with that discharge water. Whereas what you can do is on an MBR process, depending on how you want to do it, you can even eliminate primary clarification like you can on a conventional. But what we're looking to here is really combine the biological and a membrane process into one so that you can get really, really high quality effluent that can be either used for discharge, reuse, or even direct feed to an RO. So here in California, where I live, we're not as, even though we are pretty forward thinking about water, we're not as forward thinking as it is in Canada. So we know a lot of them use MBRs up there. So again, it really just gives you a good quality effluent water for discharge. And it combines a lot of the processes together so that you can really shrink the size of that total treatment process. So you may be thinking, well, why would I want to go through all the extra effort of an MBR? Really, it comes down to that effluent water quality and what it allows you to do with it. Obviously, some of these parameters are driven by the biological process ahead of it and partially removed by an MBR. Things like BOD, if they're in a soluble form, are obviously going to pass through our membrane. But if it is bound up to other solid particles, then it can be removed. And then things like suspended solids and turbidity are really what the MBRs are honing in on to remove those. So again, we can have a nice quality effluent. And I'll touch on it in a minute, but one thing that I did mention on the previous slide is we do like to stress that MBR is a process. It's not a product. So expecting to be able to drop a membrane bioreactor into, let's say, a secondary clarifier and just make an MBR start working, while it's possible, it's not really always going to work that way. So it is really important that you consider the process as a whole. And the reason I mention that here is because some of these limits like TNs and TPs are also impacted by our biological process ahead of it. So that is really important to remember that the MBRs are really geared towards suspended solid and turbidity removal. So they do have different operation modes that you can do. Obviously, there's gravity and there's pump operation, pretty straightforward. There is obviously I have suction mentioned here, but I do know that there are external MBRs in the market that are pressure driven. And so we'll touch a tiny bit on them, but not a huge amount, because obviously we really specialize on the submerged side. And then also it's good to mention that not all submerged MBRs can use both operations. The flat sheet membranes can, hollow fiber are typically limited to something on the pump operation side. Just to touch really quickly on the mechanism of filtration resistance, this is not unique to our membrane. It's pretty much all MBR membranes are going to experience this, and it's really how you see fouling start to affect the system. What we're going to see initially is that cake formation. So you can see in this initial bit here, you get a nice loose conglomeration of particles. They're not really bound together very tightly. They're really kind of there loosely, and that can be removed by aeration. So you can slough off those cake layers and obviously maintain membrane performance. If you start to lose aeration, that's when you start running into the other two problems of clogging and consolidation. So obviously membrane clogging is going to be next. We've got these little particles in the presence of the membrane, and so they're going to start passing through the pores eventually if they're too small and really our particle size isn't optimized in the MBR. And those will start clogging those pores, harder to get out. And then once we start losing that flow, the next step is cake consolidation. And as you can see here, what that really means is that cake is now going to squish together and form more of a compact layer that's really not removable by the aeration. And so this is really one of the parts that you really want to avoid, because as you can see, that TMP is going to start to spike quite rapidly once you get that cake consolidation. So we expect cake formation due to the fact this is a really high solids application in MBRs. But again, the main point is the aeration is there to remove the cake formation before we end up with any consolidation or clogging. So some of the critical operating parameters that are surrounding MBRs in general, I'm sure these are not unique to Submerged, is effective pre-screening is absolutely critical. So if we have long fibrous materials, or even, it's unlikely, but even if we have heavy damage the membranes, it's really, really important that we effectively pre-screen those to remove them from the system so that they're not essentially ruining these nice fragile membranes. The next thing is sludge health. It's kind of funny how often we actually run into this and don't see people testing for it, but essentially what we're looking at here is how healthy is that sludge in the sense that it will be easily filterable. And so we do have what we call filter test. That's what this thing on the right-hand side is showing. And essentially what we're doing here is this really quick gravity test. You just put some of your MLSS in the cone and you measure how much water falls out. And that really tells you how easy that sludge is going to be to filter, which is obviously highly important if we're filtering it through a membrane. Maintaining aeration, I'm going to say, is one of the most critical, if not the most critical. You can get away with some of the others being not optimal and still be able to run, maybe not the happiest, but you can still run it. But if you lose aeration, like we discussed on that previous slide, is when you're going to start running into a lot of these other problems like cake consolidation and clogging of the membrane. So aeration is absolutely critical to maintain properly. And lastly is prevent the airlock of the pump. This is more of just an operational nuisance that we see. A self-priming pump can help you eliminate this issue, but again, we're really just looking at it as more of a nuisance than anything. You can also use things like an adductor to kind of suck the air out as needed. So a real quick demonstration on how the aeration works. I won't focus too much on the first video. I'll really bump to the second one because it's more of a close-up. The real reason that we like to show this one is because it gives you a really, really strong idea of the new modifications that we've made to this NHP, kind of making it almost, I wouldn't call it a hollow fiber, it's definitely not, but the flexibility gives it kind of a hollow fiber-esque quality in that it will move around and it helps really remove that sludge, that if it does cake form in there, we can help with that aeration, get rid of it. And the last video, I really like this one because if you look closely, you can actually see a lot of the cake coming up and out from between the membranes. And again, this is just really to hit that point home that as long as we keep it in just a standard cake formation, we're not so bad. Once we get into that consolidation step that we're really squishing it into the membrane surface, obviously we're going to have a much harder time removing it and require things like a physical hose or something like that really to wash that sludge out. So how do MBRs manage the fouling? Obviously on the flat sheet and the hollow fiber, there are some commonalities, but there are a few differences as well. On the flat sheet side, the nice thing is obviously they both got aeration on the hollow fiber and flat sheet, but on the flat sheet side, we have a few different, I guess you would say, configurations of air that we can offer. The standard coarse bubble, which everyone's pretty used to, and then we've got medium or fine bubble as well. The nice thing that's good about the medium and the fine bubble that we can offer now is that they're both, I wouldn't say clog free, but they're kind of the EPDM sock style. So they really don't clog like a coarse bubble would, where it's just a pipe with holes drilled into it and you can get sludge intrusion into them to clog it. And so again, using those medium or fine bubble are really, really good options to make it a much more operational and friendly system. And the medium bubble actually brings us up to the same flows as the coarse, so it's kind of nice as that. On the aeration side for hollow fiber, the one benefit they have, and we'll touch on it a little bit later, is they do have intermittent aeration depending on which configuration you have. And some manufacturers even have unique leap type things where they do one big bubble or things like that. Hollow fiber, the one unique aspect is you can backwash it. The one downside to this is obviously you do lose some of your recovery, and backwashing does make your sequencing of the system quite a bit more complicated. On the flat sheet side, you think, well, if you're not backwashing, how are you getting rid of those solids? We do have a relaxation step. Essentially, we just turn the filtration pump off. We'll do, on an average application, we're looking at 9 filtration and 1 minute relaxation. And again, that relaxation step is really to do what we showed in that previous video, to let that cake formation just really get removed from the membrane matrix in between them. And then lastly, both of them obviously have a chemical CIP option, more on an as needed type of basis for both applications, but it is an option for both. So real quick breakdown into the advantages and disadvantages of each. I may have some biased opinions, obviously, but we'll put that to the side for now. And one nice thing about flat sheet is, as I mentioned before, you can operate in either suction or gravity filtration. So it's nice, and that gives you flexibility. They are extremely easy maintenance in the fact they're very minimal moving parts. You really just have your membrane block, and then you have your filtration pump, a few valves, and your aeration blower. So it's pretty straightforward and simple, very minimal sequencing. They can also operate at higher MLSS values, so that's a nice thing, which we'll touch on later. One of the disadvantages to flat sheet is, and we'll be pretty honest, is that our slightly lower packing density and energy efficiencies make us a little less competitive on large facilities, typically anything larger than 5 MGD. Their intermittent aeration is one of the big reasons for less energy usage. Obviously, we are 100% aeration all the time, so that is one downside. Obviously, on the hollow fiber side, we do have improved packing density and energy usage, and backwashing is possible. But depending on who you are, you could think backwashing may actually be a disadvantage because it does reduce recovery. And also the fact that hollow fiber have to operate at lower MLSSs do require a larger pretreatment basin. So I'll touch on that a little bit later, so I won't go too much into it. But next, external. Again, I'll be pretty frank here. We don't have a huge amount of information. A lot of the companies are a little smaller, and we don't see a huge amount of them. But one thing that we can see is operational flexibility, given you have the ability to push at the pump or pressure. The pump gives you a lot more flexibility to push water through that, especially on nasty applications. Cleaning is another aspect. Given that they're external, you can clean them pretty aggressively and not risk your biological contaminant, or basically ruining your biological portion of your process, and ease of membrane replacements as well. The downsides to them: low packing density, which means that it limits cost and scalability. And some technologies, depending on if they use aeration or not, I know some are horizontally mounted versus vertically mounted, would have a higher energy usage due to both the aeration and the pumping. So as I mentioned before, just to give you a kind of visual show of what the flat sheet versus a hollow fiber MLSS difference really gives you, you can see here on the top we've got our flat sheet MBR, and typically we operate on the low end would be 12 grams per liter or 12,000 milligrams per liter. On the high end, we're looking at 18. As you can see, the hollow fiber on the low end, you're looking at around 4, all the way up to potentially 10. And really what this means is, while our packing density may be a little lower, and I will admit I kind of didn't size this correctly, our membrane tank should be a slight bit bigger because our packing density is a little bit lower. The overall treatment process footprint can actually be much smaller due to that higher operating MLSS. So if we were to compare something like 12,000 versus 4, that means that our primary process can be 1/3 the size as it would be for a hollow fiber system. And looking a little bit about side-by-side operating comparison, I will say this is a nasty industrial application, and that's really where, not that we shine, but we tend to really see the difference between hollow fiber and flat sheet. Obviously, our flat sheet work great on municipal things as well, but you can see the one downside to the hollow fiber is, due to all the little fibers, you do have a potential to collect a bunch of foulants up at the top of the headers where the aeration is pushing it all, whereas on the flat sheet, we can kind of slough all that off and we don't run into that same issue. And as you can see, that's what results in the TMP difference. So you can see the hollow fiber had a much more rapid TMP increase versus the flat plate. And another nice thing about the flat sheet is, if you do get yourself in a bad situation to where you've completely plugged it up and you look like the hollow fiber, it's much easier to rinse them off with a low pressure hose and not damage the membrane than it would be for a hollow fiber, where you risk the damage or the potential of breaking membranes a little bit easier. Really quickly, the only reason I like to touch on this one is to show, obviously, we have been improving our packing density to get closer to some of our big competitors in the MBR space. I will admit, as we have already, that the energy consumption is a little bit higher due to our continuous aeration. But again, we're getting closer and closer. And it's one of those things where, for small facilities where you're really looking for a simple, robust process, going with these flat plates just make it so much easier because there's so few moving parts and so few things to troubleshoot really. I'll touch on this just really quickly to show you a little bit about the flexibility of our modules. Obviously, we've got various different sizes, and the one nice thing about them is they're all essentially stackable. So it kind of gives you the flexibility of messing around with how you feel fit. The smallest one on the left-hand side would be perfect for containerized units. That one in the middle, the 300S, is perfect for municipal applications. And then that one, the double high, the 600D, is perfect if you've got minimal footprint and you're really, really trying to optimize how much membrane area you can get into that small space. And lastly, what we'll touch on is if I've got a conventional multi-step, maybe secondary treatment process, and I really, really wanted to do MBR, how difficult would it be for me to do that? And in reality, it's actually pretty simple. Many times we can actually retrofit a secondary clarifier to become an MBR basin. And what this means is now you can make your current secondary clarifier, both your secondary and your tertiary treatment, all in one step. You don't need to increase the facility size. So it really makes it a nice retrofit potential if there's the opportunity. Obviously, it's not an option for all plants depending on the tank configuration of the clarifier, but I would say 80% of the time, maybe a little bit more than that, we are able to directly retrofit a secondary clarifier. And again, it just gives them the ability to have excellent quality effluent. Maybe they want to go to RO for advanced reuse and they can use that RO permeate for some processed water within the facility. Again, it just gives them a lot of flexibility. And that's it.
Excellent. Thank you, Charles. That was quite a lot of information to be packing within, those 18 minutes. I think we were like right on time too. So let me move over to my screen here and make sure I can see this. So we did have a lot of questions that came in over the chat, and thank you for that. I actually have a short list of questions myself, but maybe we can go over the ones that came over the chat box here. 1 second. Let me see if I pull them up. So one of the first ones that came up was from Tom here. It says, do you use intermittent aeration or continuous aeration?
So for the flat sheet on our side, we do continuous aeration. The challenge, obviously, as I mentioned, is if we at any point lose aeration, we start to get cake consolidation, and that's where we run into performance issues. So on the flat plate side, we are looking at continuous aeration, which is why the energy usage is a little bit higher on large facilities.
Okay, and next question here is, can you speak generally about the advantages and disadvantages of having the membrane in a second reactor or in a separate reactor, like a separate compartment?
Yeah, and so I guess the big disadvantage is it makes your process design a little more complicated if you're trying to do all the denitrification, denitrification steps. It can still be done. It's not like it's that big of an issue. One big advantage is if you include them in the same basin, and you can do this if they're in separate ones as well, is you can actually take advantage of the MBR aeration as part of your aeration oxidation process for the against the activated sludge process. And then when you cycle that back to the front end, you can do the other part. So you can take credits from the aeration on the MBR side if you have it within your main basin as well. So it's kind of, there's not major drawbacks or benefits to both sides. It's really how the facility should be designed. There are some small benefits to each one though.
Okay. I have a couple questions here of my own. So the first one was, you talked, of course, comparing flat plate to the hollow fiber. What does that make to maintenance? What does the maintenance look like between the two?
Yeah, so the maintenance is if you're talking just day-to-day, it's fairly similar. I guess the one challenge comes into troubleshooting. Obviously, the hollow fiber being they backwash, they have a lot more valve sequencing. They can be a little more complicated. Whereas on the hollow fiber side, it's literally just we filter or we don't. Either the pump's on or it's not, and the aeration's on all the time. So sequencing is quite simple there. The other challenge is with a hollow fiber, since you have so many fibers in there, if one of them breaks, isolating that individual fiber becomes a bit more complicated. On our flat plates, all you have to do is drop the liquid level down so you can see these. We have clear tubes on the top of each one, and that tube will be a nice nasty brown color, and you can say, oh, that's definitely my bad plate, and you can isolate that one individually without much difficulty in comparison to the hollow fiber side with pinning it.
Okay, and then I had one here was, this is actually something I was emailed in before the webinar, so thank you for that. So what can we use some of these MBR membranes for dewatering sludge? Yes,
we can, and we actually do have a few applications where we are doing sludge dewatering. There are limits though. The MBRs can't push it to what you would see in a typical sludge dewatering application. The highest I've seen, I would say reliably achieved, is right under 3% solids, is what we've been able to push it up to fairly reliably. I want to say it was right around 28 or 2,800, sorry. Yeah, 2,800, sorry. 28,000, was having a moment, I could not say that one number, MLSS. And so, yeah, we can do it, but there are limitations to the solids content that we can push it to.
Okay. And because we're getting pretty short on time here, I've got the last one here, was industrial applications. Would you use one versus the other if it was an industrial application for wastewater?
Obviously, I'm a little biased, so I would say most certainly I would use flat plate. But the reason I say that isn't because it's the technical advantages. The hollow fiber has more potential, especially on industrial application. We all know industrial tend to be the nastiest ones that we run into, and you run into a lot more. You have to be much more cautious about the solids. I guess you'd say screening to make sure that a lot of bad things don't get to the hollow fiber, whereas the flat plate can handle it a little bit better than the hollow fiber could. And so in general abuse that you can put to them, the flat plate can handle more abuse than a hollow fiber could, I would say.
Okay. Oh, I've got one last one here from Andrew. Can you speak generally about where to take recycle for nitrification, denitrification?
Yeah, so obviously it's going to depend on how the process is designed, but if you have everything in one basin, it makes it a little bit more complicated for it because you don't have the anoxic zone. You can put it in the front, and when you recycle your MBR, I guess you would say MLSS, back to the front end, it's going to have some DO. But essentially that's how we've seen it done a lot of times, is they'll kind of stagger it to where they allow that aeration to be minimal to where they pull the sludge off, and then that way they're not transferring a large quantity of DO to the front end in an anoxic zone for that nitrification, denitrification process.
Right. Okay. Well, thanks again, Charles, for doing this. This was great. It's a lot of information within 20 minutes. I included both your contact information and mine. If anybody does have any more questions, please make sure to send them an email. If you want to stick around, we'll be here for another 5 or 10 minutes. I keep calling it the after party, but if anybody does have any more questions, we can do that. At that, we'll wrap it up. Last bit, of course, I do want to thank you so much for your time, but at the same time, I love the idea that you said MBR is not a product, it's a process. And I think that's something that's very important. I keep thinking of it as like, okay, an MBR is a product. I'm like, no, it's a whole process. It's a whole thing that kind of works, and the way that the technology works around that. So thank you very much for that. With that, one last plug here. We do have a YouTube channel. All these webinars are on there. So if you've missed one or you want to share one, please make sure to go in there. This one will be posted here by tomorrow or potentially early next week, and everybody will get a link with that. So thanks again, Charles. And with that, I will see you again in 2 weeks. Goodbye, everyone.
Thanks, everyone. Appreciate your time.